My whole teaching career, I was under the impression that being a good teacher involved sending students off to discover and inquire about the learning they were doing themselves, and that the more independent they could be, the better. And so it was quite a shock to me when I first came across Rosenshine's 10 Principles of Instruction, and I pretty much was told the logic I was using to teach was based on some flawed assumptions. Rosenshine outlines 3 stages of instruction. The first as being the introduction of new information, guiding students in practice, and then more independent types of practice. It's like when riding a bike. You might show a student how to ride, you then guide them in practice by putting stabilizers on their bike, and finally you get them riding on their own, falling off and making mistakes during independent practice. The first thing Rosenshine identifies is that when introducing new information, we need to make sure that we understand how the individual lesson that we're teaching fits within the big picture of our subject, how it's almost like a small puzzle piece, helping students to learn to be experts. The first piece of advice Rosenshine gives is that we must break new information down into small steps. After each part or step, we need to get students to engage in guided practice. If you wanted students to learn how to summarize a paragraph, you could get students to find the topic sentence. You could model this to them and think aloud as you do it. Then, you could get students to spot topic sentences themselves from a range of different sources. Once students have mastered topic sentences, you move on to main ideas within a paragraph. You model to them how to find these, and you think aloud as you do so. Then, over to the students, who are asked to spot not only the main ideas, but also topic sentences. Finally, you introduce the idea of supporting detail. You model to the students how to find this, and think aloud as you do so. And then, engage the students in guided practice, finding topic sentences, the main ideas of paragraph, and the supporting details. In other words, we've taken a complicated task, we've broken it down into its parts, and asked students to practice after each one. In this method, there is no room for students stabbing in the dark. What we're talking about here is an idea called explicit instruction. Rosenshine came up with this idea drawing on the work of Clark, Kirshner, and Sweller. He says that when we introduce new information, we need to make sure that there is no discovery, ever. When I first heard this idea, I felt like it was an attack on the idea of group work and problem solving. But it's not. Group work and problem solving are fantastic strategies for teachers to use. They're just for guided practice and independent practice, not for the introduction of new material. This idea that I never get students to discover new information. This is a big change. And any big change that we're trying to make in education really does require big evidence to support it. And I think on this particular issue, there is quite a lot of good evidence to support the idea that explicit instruction is really effective. So where does that evidence come from? Well, firstly, there are control trials. Mayer looked at all of the control trials involving guided practice between 1950 and 1980. Every one of them was rejected. It was a slow technique for delivering content. Because it had been rejected so wholeheartedly, it was reborn in the 1980s under different names. And from 1980 until 2010, it was called discovery or inquiry-based learning. And during the same period, it was rejected again and again and again. One of the most worrying parts of this comes from a guy called Richard Clark. He analysed 70 different studies exploring discovery learning, looking at progress and comparing this to students' prior attainment. He found that those students with low prior attainment made much less progress when using discovery learning than those with high prior attainment. In other words, the achievement gap, when you use this approach, gets bigger rather than smaller. The second set of evidence comes from the work of cognitive science, and it describes how the architecture of the human mind fits quite well with explicit instruction. The first thing we need to do to explore this argument is to consider what learning is. Learning is a change in our long-term memory. If nothing's changed in your long-term memory, then nothing's been learnt. We can see the importance of long-term memory by looking at the example of chess. Mastery in chess involve 2 skills. Firstly, you need to be able to reason, and secondly, you need to be able to store a huge number of games in your long-term memory. Now, by playing blitz games, which are these really short chess games that only last 1 minute, this completely takes away the possibility for reasoning. What was interesting was that the same people that were good at chess in the normal leagues when they had around 10 minutes to play each game were exactly the same people that were good at blitz chess, suggesting that long-term memory is really the determining factor in how successful a chess player is. Now, if we take this idea that moving new information into long-term memory is the real goal of a teacher, then to get information into long-term memory, it needs to pass through our working memory. That's the conscious processing part of our mind. So let's take, for an example, known information. Now, this is already in our long-term memories, and it takes up very little processing power when we encounter it. For example, if you're an expert at maths, it doesn't take you a second to do your times tables. You don't have to put any mental effort in. However, when new information is introduced, this places a much greater strain on our working memory. And this means that we need to be really careful when we're introducing new material to novices to make sure we don't overload their working memory. And at this point, it's worth comparing unguided instruction with explicit instruction to see why explicit instruction is a better fit with our cognitive architecture. So if we compare two groups, those taught with explicit instruction, where modelling and explanation are used, the other taught with trial and error, we can see which is more effective. Modelling and explaining takes away all of the mental effort of trial and error, and it allows information to pass into our long-term memory much faster. For example, if you want to get better at chess, you need to know what black is going to do next. Black is one move away from checkmate. Now, there are three solutions, and if I used explicit instruction, I would simply show you what they were, and as I did so, explain why they would work. On the other hand, I could just leave you up to your own devices, and you could sit there for hours trialing and erroring different possibilities and trying to work out what's best. Now, that might work as well, but it will be a hell of a lot slower, and all of your mental effort would go into the activity of trial and error rather than storing 3 simple rules of what to do next in your long-term memory. And we can apply this widely to our teaching. So in summary, both control trials and our cognitive architecture seem to imply that when we're teaching novices to understand new information, explicit instruction works best. So what does this mean for my classroom practice? Well, in the past, I would have set activities and constructed activities to allow students to discover and explore. And now I need to work on something that's a bit more dynamic, my ability to explain things to students in a clear and concise way. I also need to work on modelling to my students. Now, in terms of doing these two things, I think there's some tips that all teachers can benefit from. The first is, if we look back to Rosenshine, the idea of breaking things down into small steps. Now, this isn't suggesting that we should start lecturing to our classes for lengthy periods of the lesson, because after each step, remember, the students should be engaged in guided practice. And I think the reason why explanations are so important is because they take abstract ideas and it makes them concrete, so that novices can understand them. Now, when you're introduced to something new for the first time, it's very often the case that you remember the analogy or the example your teacher gave you, rather than the idea itself. Another really important tip when it comes to explaining is the use of visual modelling. So we can take a Lego brick, break it down into its parts in order to teach students about fractions. Another important finding from cognitive science is the combination of visual and auditory content works really well together. Now, the idea is that if you speak and at the same time give students something to read, this is going to really strain their working memory. One of the easiest wins when it comes to explanation is just to cut out all the nonsense from your PowerPoint. In the past, I've been so keen to impress anyone observing my lessons that I would put 15 different things onto every slide. The consequence of this is that it really puts a lot of pressure on a student's working memory and doesn't allow them to focus on the one thing I'm trying to teach them. Students will have no hope paying attention to us if we've got thousands of images on our board. We need to cut these down to the basics and make sure we communicate in the clearest possible way. Another important part of explicit instruction is the role of modelling. In other words, we don't let students guess and make mistakes, but we show them in very careful steps what exactly it is we want them to know. When introducing a new process or idea to students, I will now start by modelling. This involves me telling them step 1 is this, step 2 is this, step 3 is this. Now I'm going to show you me solving those 3 steps, then we're going to do one as a whole class, and then you can go and do it on your own. Doing it this way reduces the chance for error. Rather than practicing mistakes, students are actually focusing on remembering the rules and steps needed to solve a problem. The idea is that this explicit instruction in the early stages drills students so that later they don't need these steps, they're just automatic to them. Another really important part of the modelling process is to show students your thought processes. Now, this often involves explaining to students the decisions you're making when you're solving problems. Modelling can also be taking all the information that students could possibly know about a topic and organising it for them. For example, when teaching To Kill a Mockingbird, the teacher might select the quotes that build to a particular argument. By modelling this to students, they're far more likely to spend their mental effort internalising it than they would be if you asked them to discover it for themselves. Once they've mastered recalling this first example you've given them, they can then be guided in practice constructing their own arguments. One of the biggest gains that I've had from changing to this more explicit approach to instruction has been that students in my class aren't making the same silly errors again and again and again. In the past, because they were discovering, they would all make similar sort of errors as they tried to figure out how to solve problems, and I would have to go round like a broken record fixing the same issue over and over again. By being really clear about the steps and guiding them in practice, students aren't making the foundational errors and mistakes that they once were. Instead, they're working on refining and practicing the skills that I've given them.